So today I'd like to tell you guys a little bit of a story about some research going on in my group, where the focus is on asking the question whether or not it's possible to utilize quantum mechanics to make better measurements. And my main goal of this talk is to really carefully lay out the nature of the question, and then eventually at some point, maybe to get to a little bit of a conjecture that my group and I have been thinking about in terms of a particular type of entanglement known as spin squeezing. You will find connections to a variety of talks that you've already heard about. I'd like to think that there's some sort of a merging of ideas from both Ivan and Ruth's talk from yesterday. But yeah. So today's story is broadly about a topic within my tribe that people call quantum metrology. And here, quantum these days is often used as an adjective in front of a number of other words, including computing, cryptography, simulation, etc. And the focus of my talk today is actually on quantum sensors. So it's really on asking about using quantum mechanics to do particular measurements and sense particular observables. And I think as the audience is broad, I think it's very important to always ask the question, what exactly is quantum mechanical, and why is quantum mechanics either relevant or possibly useful in this particular context of sensing? And I might argue that there are two very natural motivations for thinking about quantum mechanics within the context of sensing. The first is very experimentally motivated. Yeah.
Can I switch on the volume up a little bit?
Volume up, yeah, sure.
You can maybe, sure.
I can also talk louder. I'll talk a little bit louder. Sounds good. Okay, fantastic. That's usually not a problem. You usually talk less loudly, at least by my wife. Motivation one, I think, is kind of experimental in nature. And you might think that at some level, if you're interested in sensing signal variations in an extremely small length scale in general, maybe you're interested in resolving the texture of nanometer scale magnetic fields, then your sensor had better be small anyways. And if your sensor's that small, maybe automatically its rules are governed by the rules of quantum mechanics. Reasonable. A second motivation, which is the motivation that I'll focus on for most of my talk, is a question of whether or not it's possible that correlations, and in particular quantum mechanical correlations in the form of entanglement between multiple sensors, can enhance the sensitivity of measurements beyond what is allowed classically. And here I'll start by emphasizing a sort of a very obvious thing relating very much to Ivan's central limit theorem. Typically, if we think about going from a single individual sensor to multiple sensors to an ensemble of sensors, one just from the central limit theorem, the narrowing of a distribution, has a sensitivity that typically scales as 1 over the square root of the number of sensors. I should emphasize for just one second that here, I'm talking about sensitivity, not accuracy. So I'm assuming that if you have an experiment, you've designed an accurate experiment to get the right answer. And sensitivity is focused on how many measurements does it take to resolve a small change in the variation of a particular parameter. Okay? And of course, indeed, in our classic world, we expect that sensitivity scales as the square root, 1 over the square root of the number of sensors. And here, one of the focal points of this talk today will be to ask the question whether or not quantum mechanics can allow us to do better. And if it can allow us to do better, how does it allow us to do better, and what is the intuition behind that better? Before getting there, I'll start with a little reminder of one of the central results of classical estimation theory. I think something many of you will be extremely familiar with, known as the Kramer-Rao bound. But to get there, let me make the problem extremely clear. The problem that we're interested in is very simple. We're interested in calculating an estimate, theta hat, for a particular parameter theta, given, for example, measurements x, or a series of x's, from a particular probability distribution p of x, which depends on theta. That's the nature of the problem. And I would say that in the search for truth from many different distributions of opinions, there's a very nice quote recently from S. Person, which I think is interesting. It says, "In these democratic days, any investigation into the trustworthiness and peculiarities of popular judgments is of interest." I suspect that some of you are laughing because you know that this is not from some person in 2025, but instead is a quote from Francis Galton in 1907 in his Nature paper Vox Populi. And indeed, the sentence right after that first sentence is that the material about to be discussed refers to a small matter, but is much to the point. And what Galton subsequently describes in this very short Nature paper is his observations at a state, this is true, his observations at a state fair about a cow weight guessing contest. And so this particular, this is no joke, you can look this up. So in this particular example of the cow weight guessing contest, theta, the true value of the cow, I'm putting some number here, is given by the theta here. And you can imagine that samples are the guesses from individuals. And for example, if one only has a single individual guess, that gives you one measurement from that probability distribution, which is human knowledge of cow weight. I suspect that modern society would do much worse. But in 1907, this is a very good estimator, okay? So if one only has that one measurement, then the only way you can make an estimated value is just to take theta hat as that one measurement. But it's completely unsurprising to any of you that in fact one can do better by taking n repeated measurements and simply taking an average of those measurements as the estimator for the true value. And indeed, that was the observation that Galton made, that actually it was surprising that nobody quite got the cow's weight exactly right, but the average was very, very close, actually. So it turns out that one of the central results of classical estimation theory is known as the Kramer-Rao bound, and it tells you about the variance of this estimator or any such estimator. And in particular, it tells you that the variance of the estimator is bounded by value c over n. Yeah, Lynn? Oh, sorry. I thought you were about to ask a question.
I'm biased.
Okay. You're okay.
I'm biased.
Yeah, unbiased. Yeah, exactly. I'll be able to say that in just a second. Unbiased, absolutely. Yeah, as I said. So I think the Kramer-Rao bound has kind of two pieces of content. One which is supernatural and immediately connected to your own intuition, to what Ivan said. This is a variance. So the standard deviation of an estimator goes as 1 over square root of n, central limit theorem. The second piece of information that is contained in the Kramer-Rao bound is that the C coefficient can be exactly computed. It's 1 over something known as the Fisher information, and the Fisher information knows about both the kind of width of the probability distribution as well as the rate of change of that probability distribution with respect to changes in the parameter theta. Okay. So it turns out that, as Ivan has beat into us in the last talk, the key idea kind of from the Kramer-Rao bound is that sampling a distribution always leads to noise. And in particular, here we're thinking about noise on the estimates that we're trying to make. So as sort of was already mentioned by Lynn, in this case, we're thinking about the Kramer-Rao bound applies to unbiased, uncorrelated measurements. Of course, when you have correlated measurements, it's very hard to make any bounds. The guessers could have agreed beforehand to all guess the same value for the cow. So once you have correlated measurements, it's hard to say anything. So there's a particular restriction to the bound in this case. So with that reminder for all of you, let's move on to a setting that I'll try to introduce in quite slow and in quite a lot of detail, which is the exact analog result in quantum estimation theory. And already the rules of the game when we think about quantum estimation theory are slightly different than the rules of game when we think about classical estimation theory. In particular, the problem starts off being the same. We're interested in calculating an estimate, theta hat, for a particular parameter theta, but now the thing that we're given is some quantum state rho of theta. So what do the rules of the game look like? I mean, and this is, I think, very reasonably experimentally motivated. This is, kind of the rules of the game that you'd imagine actually doing a quantum experiment to be able to probe some small signal, for example. You start by preparing maybe use this one. You start by preparing some probe state. I'm representing here things as a density matrix rho. And then, in order to somehow allow the probe state to depend on the parameter that you're interested in theta, you evolve that probe state. Here, I'm writing down evolution under what's typically called the Heisenberg evolution picture, where I'm conjugating my initial density matrix, or my initial quantum state, by a unitary operator. That unitary operator typically defines time evolution. And we're imagining that physically what's happening is that you have a quantum state, and now it's evolving under a field. That field has some knowledge about the parameter theta built into it, and that means that the unitary that you apply to this particular quantum state also has some dependence on theta. And that naturally now gives you an output state rho, which itself depends on theta, and all you can do is now measure some observable. And you can ask yourself, if I try to optimize over measuring all different possible observables, what exactly would be the most sensitive measurement that I could make? One important thing to emphasize is that this measurement especially in the context of quantum mechanics, immediately gives you a distribution of outcomes corresponding to the eigenvalues of that particular operator. And those outcomes depend on theta, the parameter or the field that was encoded in the evolution of your initial state. Okay? So let me try to illustrate this particular chain of rules of the game with a very, very simple example. Example will harken back to your, I think many of you from high school remember, if you have a little magnetic dipole and it's oriented in a magnetic field, and the dipole will sort of precess, and that precession is known as Larmor precession. This type of Larmor precession is actually one of the very, very standard ways in atomic physics or in atomic spectroscopy to measure external fields. For magnetic dipoles, we'll talk about magnetic fields, but this could be any field that allows a particular quantum state to accumulate a signal. So let us try to get our feet a little bit wet using a very, very simple example. And in particular, you can really think in your mind about that classical magnetic dipole, like a very small bar magnet. But since I'm thinking about a quantum degree of freedom here, I'm really going to think about a quantum spin degree of freedom, the magnetic dipole in this case. And the spin is going to be a two-state quantum system. The two states of the quantum systems are going to be spin up and spin down, represented in ket notation as follows. And it turns out, as I know many of you are super familiar, a very nice representation of the different allowed superposition states of a two-level quantum system is to map those states onto the two-sphere, also known as the Bloch sphere in many contexts. And so, for example, here, the north pole would be corresponding to the state spin up. The south pole would be corresponding to the state spin down. And if you have a spin state oriented in the equatorial direction, that corresponds to a superposition state between spin up and spin down. Just making sure that notation's clear. So let us imagine a very, very standard, for those of you who are experts, a Ramsey spectroscopy type of experiment. We can imagine the following setting. Let's imagine taking a single quantum spin degree of freedom and orienting it in the x direction. That x direction, as I just said, is a superposition of spin up and spin down. And now what's going to happen, given that I have an external magnetic field in the z direction, is that this little magnetic dipole or quantum spin will precess in the equatorial plane. And if I time my experiment very carefully, so I know t, how long I allow the signal to be accumulated for, and I can measure the angle theta very precisely, then dividing the two up to units, gyromagnetic ratio and stuff, that gives me immediately the strength of a small external magnetic field B. It turns out, somewhat unsurprisingly, that if you take a single shot measurement, for example, you project along some axis in the equatorial plane, you actually get very little information out of this type of measurement. And that's represented by the fact that the likelihood or probability of getting one of these results has a pretty broad distribution. I mean, it is centered on the fact that theta hat, the estimated value, is equal to theta. So it's centered on 0, but it has a pretty broad distribution. It turns out, again, coming from central limit theorem, forgetting any quantum mechanics, if I did this n times, or with n quantum spins that were all independent from each other, I would narrow this distribution as 1 over square root of n, much like you would expect for classical estimates. Turns out one of the central results of quantum estimation theory is that if we use multiple spins to do the measurement, as I said, if you have uncorrelated quantum spins, then the Kramer-Rao bound that we just said before still applies. That leads to a sensitivity, again, which is the square root of this, the standard deviation, that goes as 1 over the square root of the number of sensors. I don't know exactly why the naming convention is as follows, but that's called the standard quantum limit. Okay? So if you find a sensitivity for a many particle system, you have many sensors, and you ask, as I increase the number of sensors, but I keep the rules of the game, the state that I try to generate the same, how exactly does my sensitivity improve? If it improves as 1 over the square root of the number of sensors, then you should think about that as, in some sense, uncorrelated classical bound, and that's called the standard quantum limit. It turns out that by doing a little bit of algebra, I think one defines sort of a symmetric log derivative and then optimizes over all possible measurements, does a couple Cauchy-Schwarzes, it turns out that you can actually prove that if you have a quantum entangled state, no matter what type of quantum entangled state it is, the best you can do, so this is not all types of entanglement, but specific types of structured entanglement, but in those cases, the best that you can do is that you can get a variance that scales as 1 over n squared. this is known as the quantum Kramer-Rao bound and leads to a corresponding sensitivity that improves as 1 over n, the number of sensors instead of 1 over square root of n. So we would say this is a quadratic enhancement in the scaling of the sensitivity with the number of sensors that one uses, assuming that one can generate this type of quantum entangled state. And that particular limit, if one finds a scaling as 1 over n, at least for systems whose energy density is extensively bounded and reasonable, that's the best you can do, and that's known as the so-called Heisenberg limit for sensitivity scaling. Good. So for the next piece of the talk, I'll focus on kind of a specific type of entanglement. As I mentioned, it turns out that Hilbert space is full of lots of entangled states, and essentially measure zero set of those entangled states are thought to be useful for this type of quantum metrology or quantum sensing where one can beat the 1 over square root of n scaling. And I'll focus on a particular type of entanglement which is known as spin-squeezed entanglement. And here I'll really try to give a little bit of a feeling for what exactly is the thing that limits the sensitivity of a measurement, and I'll then try to be able to give you kind of a feeling for what exactly it is about the quantum mechanics that allows you to win. Sorry, Senka.
Yeah, horizontally, can I think of this as like n spins or my big ferromagnet giant spin? So more sensitive to the field, right?
That's right, except for the fact that you need that ferromagnet to be in a cat state. But yes, that's right. That's exactly right. So I think what Senka's saying is that, is the intuition for where this factor of n comes from. If you have these n spins and they're kind of in a correlated state where they're all oriented in the same direction, then is that where the factor of n comes from? And the answer is yes, except for the fact that you need entanglement. You have to make sure that you have the other state in the same way that we were looking at up plus down. You want to have the GHZ state to be able to saturate this. Good. Good. So let's try to now understand. I'll sort of take our example and kind of continue walking through it. Try to sort of understand what exactly is the context for this type of spin-squeezed entanglement. And here, let's return to the goal that we set out previously in the example where I sort of illustrated the quote-unquote rules of the game. And in particular, let's imagine that our goal is that, indeed, we want to measure the strength of an external magnetic field oriented in the z direction, which couples to degrees of freedom indexed by operator sigma. And the strength of that external magnetic field is epsilon, so it's a very small strength. And as promised before, you have that the spins are initially oriented in the x direction. This is perfect, look at this long arrow. They're initially oriented in the x direction. And if you imagine an experiment where there's precession, then really the way to measure this angle theta is to try to measure deflection away from x, for example. So you'd like to measure what is the new projection of that spin, for example, along the y direction. Right? Very simple. So you initially have spins like this. If they're deflecting in some way from the external magnetic field, and you want to measure the angle of that deflection, you can naturally measure it by measuring the deflection in the y-axis. Okay? So you might ask yourself, at this point, we haven't talked about, and I've prefaced the fact that it might be possible that a certain flavor of entanglement can allow us to do sensing with a scaling that's better than what is allowed by classical physics. But a question maybe to start off is, okay, fine. So forgetting experimental noise, laser fluctuations, whatever it is, what exactly limits the ultimate field sensitivity of this type of very simple precession-based measurement of an external magnetic field when I have n spins oriented, in this case, in an uncorrelated state? The physical intuition that you should have is extremely simple. It's the idea that you'd like to compare, the natural intuition is that you'd like to somehow compare the amount of deflection relative to the variance of making measurements, for example, of sigma y in the first place. Because if the variance of making those measurements is large relative to the amount that the signal's been deflected, then it's actually very hard to resolve those two distributions. But if you have a deflectant that's larger than the variance, then it turns out it's relatively easy to distinguish those things. And very important thing is that when I'm in an eigenstate, for example, when all my spins are oriented in the x direction, then taking a measurement of sigma y total, which is simply a measurement of the individual sigma y operators for each of the spins, each of those, you're no longer in a definite, if you're in a definite eigenstate of x, you're not in any definite eigenstate of y or z. And what you get is that for every single individual spin, you've got a random value, either +1/2 or -1/2, and you'll add those up, get a binomial distribution. And you'll find that here, what I'm representing here is typically called a Wigner distribution. But you can imagine that it's the distribution of measurements for n spins of sigma y total. And the point is that clearly, the most likely outcome along this particular axis is 0 because of n spins. And if there's no definite orientation in the y direction, then on average, I'll have 1/2, -1/2, 1/2, 1/2, -1/2, and they'll add to 0. But there will be an intrinsic variance associated with that particular measurement. And that variance actually indeed goes as the square root of n and is what is represented by this kind of blob. If I did the same thing in the z direction, if I measure the z operator, I find the same exact variance. And in fact, for any operator cos theta sigma y plus sine theta sigma z, I would get exactly the same variance. And that little blob you could think about as just some uncertainty blob at the edge of my arrow here. And that really is the fundamental limit when you try to do measurements like this. This absolutely limits experiments in the lab. So what happens here is now, again, if you imagine there being a small angle of deflection, if the blob at the end of this is big relative to that small angle, then it's very hard to resolve. But if you can somehow have a larger angle of deflection or make that blob smaller, then you can make measurements in a more sensitive fashion. So this particular type of noise or variance is fundamental to quantum mechanics. It's fundamental to the projective nature of making measurements in quantum mechanics, and it's typically called the quantum projection noise. In the context specifically of spin degrees of freedom, you'll hear it also being called the spin projection noise. So one can ask maybe now a very natural question, which is how does one beat this quantum spin projection noise? Or is it possible? So if you have n spin degrees of freedom, I've said that the intrinsic variance of making projective measurements to just try to read out your signal leads to noise. And if that noise swamps the amplitude of your signal, then you will not be able to observe the signal. So the idea is that, well, if one could somehow, first, I would say, maybe before reshaping, you can ask the question, is it possible to actually shrink the size of this blob? So are there quantum mechanical states that I could have, entangled states, where the size of the blob, the area of the blob shrinks? It turns out the answer to that is no. This size of this blob is limited by the Heisenberg uncertainty principle because there's these two variables, sigma y and sigma z, do not commute with each other. So that blob cannot be made smaller. But the fact that it can't be made smaller does not immediately rule out a slightly different strategy, which is if one could somehow reshape this noise, that could also be very interesting. So now imagine, for example, that again, my signal's really being accumulated as a deflection in the equatorial plane, and it's a deflection along some direction. If I could somehow reshape the noise so that it wasn't completely circular, but had a very, very long oval of this shape, then it's possible that at least along the direction where I'm trying to read out a signal, that the actual variance could be much smaller than the deflection that I'm actually seeing. And so that's really the essence. That's all the idea is for this particular type of entanglement known as spin squeezing. And it's proven that, in fact, if one has spin squeezing, which I'll describe, which I'll write down a figure of merit in a little bit, is 1-to-1 with entanglement. You must have entanglement between the degrees of freedom in order to have a particular figure of merit known as the squeezing parameter to be less than unity. So a focus of the next little piece of the talk is going to be to ask the question, how in general does one generate such a state? And the rules of the game in this particular context, again, I think we're asking a theoretical question, but I think the rules are relatively experimentally motivated, is we'd like to start with some initial state, some simple initial state that can be prepared relatively easily. You don't want to hide the complexity of the entangled state in the initial assumed state. So we assume that we'd like to start with some simple, preparable initial quantum state. And then the way I'd like to ask if we can generate such a spin squeeze state is to look at the late time dynamics under Hamiltonian evolution of a specific system. So this is certainly related to Ivan's talk. How do quantum dynamical systems behave in long time? And actually the mathematical underpinnings of trying to answer this are very much related to the hydrodynamics ideas that Ivan was sort of mentioning at the very end. So it turns out there is a paradigmatic example known since Kitagawa and Ueda in the early 1990s, where they emphasize that this particular type of structure in the quantum projection noise or the spin projection noise can be generated by time evolution under a Hamiltonian that is known as the one-axis twisting Hamiltonian. You'll immediately understand in just one slide what the geometric interpretation of one-axis twisting is. But for those of you that come from a little bit more of a physics or condensed matter background, the Hamiltonian is extremely simple, or even in many contexts. It's the Hamiltonian associated with all of the spin 1/2 degrees of freedom interacting with each other via a so-called Ising interaction. So there's just energy shifts depending on the orientation of two spins. And it's an all-to-all Ising interaction. So the interaction has the same strength over all pairs I, j. And of course, probably up to a factor of 4, depending on if I use spin or Pauli. This can be rewritten as simply sigma z total, the angular momentum for a large spin, which is just the sum of all of the individual sigma zi's. So sigma z total is sum of over sigma zi's squared, and that square probably, again, double counts the ij's over here, but sigma z total squared over n would be the representation of this one-axis twisting Hamiltonian in terms of a large spin degree of freedom. It turns out that that work has motivated really generations of really pretty experiments, especially in the context of quantum degrees of freedom in cavity-based systems interacting with light. And those beautifully engineered systems are able to very good approximation, realize, complex but beautiful, are able to realize variations of this one-axis twisting Hamiltonian. So the rules of the game we said is that we'd like to start with a very simple initial state that has no correlations whatsoever, a so-called product state. And then it turns out that Kitagawa and Ueda teach us that if we evolve this simple initial state, in fact, it's the exact same initial state we've just been looking at from the perspective of Larmor precession spectroscopy, you can ask yourself, what exactly does this quantum projection noise of this state, which we know is a Gaussian blob in the YZ plane, what exactly does it do under the Hamiltonian? And here, you can just remind yourselves that the generator of rotations around the sigma z total axis are given by sigma z total. So if you wanted to rotate by an angle theta over 2, you would apply the operator e to the I theta sigma z hat, and that would be a generator. In this particular situation, you have kind of intuitively that this theta, the angle that you rotate by itself, depends on the amplitude of sigma z total. So sigma z total is large and positive over here, smaller and positive over here, large and negative over here. It's just the value along the z-axis. And if you just imagine this type of extremely simple dynamics, and you just apply that rule, that I rotate by an angle theta that is dependent on the value sigma z total itself, then you see that, a point here moves the most to the left, a point here moves the most to the right, and you can see immediately that this type of dynamics improves the phase resolution of a Ramsey spectroscopy or a Larmor precession experiment by reshaping the quantum spin projection noise. And in particular, it kind of rotates, it sort of twists you along a single axis, hence the name one-axis twisting. Good. So it turns out that, as promised, it's kind of useful to define for ourselves. It'll show up a little bit, a figure of merit for this type of a squeezing. And it's also useful to relate this figure of merit to some of the things that we said with respect to the quantum Kramer-Rao bound a little bit earlier. So it turns out that this squeezing parameter is naturally the figure of merit for squeezing, and it cares about, on the numerator, all you should imagine is that you're trying to minimize the variance in the YZ plane. So you have a particular state that's oriented in the x direction, and this is just a minimization of the variance in that plane. So in this particular plot, it's along that direction over there. And it turns out if you want to do a sensing measurement, like a Ramsey spectroscopy measurement, you certainly don't want the length of the spin vector to decrease too much. Otherwise, anyways, you can't resolve the angle of a small deflection. And so in the denominator, you have that sx squared that measures the length of that of the x component of that vector, also should not get too small. If that gets too small, this object blows up, and this object being less than 1 is where we say that we have a spin squeeze state, and this object being less than 1 is also a provable witness of multipartite entanglement. It turns out that if you just compute in this Kitagawa, Ueda, one-axis twisting model, you can analytically compute the scaling of this squeezing parameter as a function of the number of sensors or the number of spins you have, and it scales down as 1 over n to the 2/3. This is, of course, the essence of scalable spin squeezing. It says that whatever the sensitivity will get out or whatever the figure of merit will get out gets better as a function of increasing system size. But it turns out that, of course, that sensitivity and the improvement systems is also true just for classically correlated particles. It goes as 1 over square root of n. In this particular case, for one-axis twisting, the type of squeezing, the type of squeezed entanglement that you get out leads to a sensitivity that is in between the two Kramer-Rao bounds that I emphasized. The classical one, which is 1 over square root of n, and the quantum one, which is 1 over n. So it is better than what you can do with classical correlations, but not quite as good as what is allowed by quantum mechanics. There are other examples of Hamiltonians. One is called two-axis twisting, maybe unsurprisingly, that do lead to a sensitivity that saturates the so-called Heisenberg limit that goes as 1 over n instead of this 1 over n to the 5/6. One other thing, kind of making a little bit of a nice connection to Ivan's talk, is that we're thinking about late-time physics here. I'm not thinking about the dynamics of an order 1 timescale, but really it turns out that to get this optimum value of the squeezing parameter, so the squeezing parameter has its own dynamics as a function of time. You started with some state, you're evolving it under one-axis twisting, and at each time you can ask, what is the value of this figure of merit? This value of the figure of merit improves as a function of time, but then gets worse at late times. And it turns out that the optimal time scales extensively in system size, again, in this particular analytic case, as n to the 1/3. So we're interested in, by that time, we're certainly interested in some late time hydrodynamic description of what's going on in terms of the underlying physics here. So it turns out that spin squeezing, this particular type of entanglement, has been generated in a multitude of experimental systems, in very many really nicely engineered systems. I think not all of these dots are actually spin squeezing. Some of them are different types of entanglements, I think related also to what Sanka asked, in terms of there being a superposition of two large ferromagnets. But there are dozens, I would say, of experiments having demonstrated spin squeezing. It turns out that, I don't think there's anyone that has listed here. So it turns out, I'll give you a little bit of cold water. It says, it's true that despite many such demonstrations, I think it's accurate to say that spin squeeze entanglement has never been used to measure anything better. So, and the reason for that is both fundamental, and I think there's a fundamental tension there that this illustrates in some way, which is that one can, in principle, win from quantum mechanical correlations, but oftentimes that win can be quite subtle and it might be very difficult to actualize. In particular, here's my good friend Adam Kaufman at his lab. Many of the experiments that have demonstrated spin squeezing do so in a very, very complicated experimental setup. And the complications of that experimental setup kind of stem from the Kitagawa-Ueda Hamiltonian. I need to engineer something which has all-to-all interactions of equal strength. That's not something that you often see in nature. It's oftentimes the very controllable atomic or quantum simulation platforms that have the capability to do that type of engineering, but those capabilities come at a cost, and that is in the sense that the experiments are very complicated. So I think a very natural motivating question for the rest of the talk and for the theory that we'll sort of think about is it possible that there is maybe a more universal approach to spin squeezing that doesn't involve the engineering of these one-axis twisting, two-axis counter-twisting Hamiltonians, which oftentimes one does with atomic ensembles and cavities. And in particular, my personal favorite, there's a large class of physical systems. You've already heard me say dipole more than once. And there's electric dipoles, magnetic dipoles of all different sorts. So just as an example setting, and one that we'll sort of zoom into a little bit, one can ask, if one has either magnetic or electric dipoles, things that certainly have essentially short-range interactions, there's a power law interaction. It's not strictly local interactions, but it's certainly not all-to-all interacting with the same strength. Can one still generate scalable spin squeezing? Scalable in the sense that in the scaling limit as n increases, the sensitivity improves without bound in a way that's better than what classical Kramer-Rao allows you to do. So in particular, I'll start zooming us into a particular setting that's very much motivated by dipoles. In particular, that Hamiltonian setting, that sort of equation of motion setting, is a model that's known as the long-range XXE model. something I guess Ivan didn't mention, but it's certainly related. The short-range version of this is related to many of the questions that Ivan was saying on his last slide. So the content of the equations of motion here is extremely simple, so I'll just mention it for those that are a little bit unfamiliar. There is the Ising piece of the interaction, which corresponds to an energy shift depending on whether the degrees of freedom are aligned or anti-aligned. And it turns out the XX and YY component just correspond to the fact that spins on sites I and J can exhibit what's called a flip-flop with each other. So an up-down configuration can go to a down-up configuration with a matrix element that knows about this J perpendicular object. And of course here, I'm thinking about dipoles. Dipoles have a power law that goes as 1 over r cubed, but as a theorist, I'll be a little bit more general here. I'll consider a more generic power law where I allow the range of that power law to vary, and that being alpha. And so now the question that we've zoomed into a little bit more is it possible to get scalable spin squeezing in this much more general class of systems? And then we'll zoom out even further and ask, what are the general conditions to be able to generate this type of entanglement in the first place? It turns out that a number of years ago, almost 10 years ago, there was an interesting no-go theorem. And in particular, you'll notice that the two Hamiltonians, clearly there's a difference in the range, the spatial range of the interaction. But there's also, and here the XXZ model has this flip-flop term, but there's also an Ising piece of the interaction that, at least in its functional form, looks very similar between the two. So a number of individuals, Fossfide, Gong, Gorshkov, and Clark, asked the question, what if I just consider a short-rangified version of the one-axis twisting Hamiltonian? So I move away from the all-to-all interaction limit, but I still keep purely Ising interactions, and I just go to a power law form of this interaction. So I essentially set J perpendicular to 0. It turns out there's a no-go theorem, more or less proven by them, which says that it's impossible to get scalable spin squeezing when you short-rangify the one-axis twisting Hamiltonian. It turns out that, this is kind of an interesting story of how sort of my group got into this. We sort of got into it in a way that I like to call picturology. It turns out that although it was known that for this particular short-rangified Ising model, that it was impossible to get scalable spin squeezing, it didn't mean you couldn't get an order 1 win. You get a prefactor win, but you couldn't get a win that scaled with your system size. Fine. So Anna Maria Ray's group a couple of years ago simply looked at, specifically for this long-range XXE model, there's 2 tuning parameters, the ratio of the strength of the Ising interaction to this flip-flop term, which is represented by JZ over J perp, and the strength of the power law alpha represented to the y-axis. And what they asked, they only looked at one system size, because the expectation was that one cannot see any scalable physics. So let's just look at a system size that's reasonably large for experiments and ask, what is the order 1 gain that one can get? And they found kind of a phase diagram that had some, none of these contours are sharp, but there are boundaries drawn that are kind of based on how much of an order 1 gain in a Ramsey spectroscopy sensing experiment you could possibly get, or how much, what is the value of your figure of merit, your so-called squeezing parameter. And so you find that there's a region kind of largely represented by this yellow where you get some amount of spin squeezing. Again, it's not scalable, but some amount of spin squeezing, and the sort of darker regions are where it's not squeezing. It turns out that from looking at this particular quote-unquote phase diagram, which is a phase diagram of how much metrologically useful entanglement, one immediately notices a very nice deep connection to a much more specific and sort of more easy to precisely say phase diagram, which is the ground state phase diagram for the same model. Okay? So again, the question that's being asked here is a dynamics question. It's a very simple dynamics question. It asks, as Ivan says, you start out with a quantum state and you ask, what are the late time quantum dynamics of that state? And do those late time quantum dynamics generate a particular type of entanglement known as spin squeezing, which is useful for doing better measurements? The question that's being asked here is a much more classic StatMet question, which is if you take a system, this particular Hamiltonian, down to 0 temperature, is there magnetic ordering in the system? And in particular, the XY ferromagnet here corresponds to all the spins aligning in some ferromagnetic way in the XY plane. The Néel antiferromagnet corresponds to spins aligning sort of opposite to each other. And then the Ising ferromagnet corresponds to spins aligning out of plane in the Z direction. It might be hard for you to see that there's a deep connection, but with the magic of, and because this is alpha here, 1 over alpha here, it turns out they flip JZ.
You have a question?
Yes.
Use your microphone.
They defined it, in their Hamiltonian, they defined it with a minus. I'm about to do that. Yes. So Teng is very, very sharp. So it turns out, relative to the, relative to the convention that I'm using, there's actually a minus sign here. So with the magic of PowerPoint, let me help you do that. So I flip it, and now I've also changed the alpha axis to be 1 over alpha. And now you see that there is some topology of this phase diagram that doesn't immediately seem unrelated. At least there's some arc where the nail state doesn't have this type of spin squeezing, and there's some intermediate region where there is. Okay? So from this, it turns out, and of course there were lots of other ideas floating around at the time, but from this one can make a very simple conjecture, which is maybe finite temperature continuous symmetry breaking. That's a statement about the nature of low temperature magnetic order for a particular Hamiltonian. Maybe that has some, in this particular case, it's clearly related to something like the XY ferromagnet. It may be that's somehow related deeply to the ability for the same Hamiltonian to be able to generate some form of spin squeezing. And again, I emphasize that these are two very different questions that we're asking. One is a phase diagram about dynamics from an initial product state. The other is a StatMech question about the nature of magnetic order at low temperatures. So the first question I think many of you, I think, will have is, well, in a typical dynamics question, we don't usually, you have a pure starting state. You don't usually talk about the temperature of this. So what exactly do I mean when I talk about finite temperature symmetry breaking or finite temperature order? So let me start by kind of operationally defining for you what exactly is the notion of temperature. How do we fit that idea into the spin squeezing protocol? And it turns out the idea is very simple. From our initial starting state, we can measure the energy density of the starting state with respect to the Hamiltonian, and then we simply match. We take all of the Gibbs states of that Hamiltonian, e to the minus beta h, we compute the energy density of those Gibbs states, and under thermalization assumptions, you assume that the dynamics of this particular initial pure state will ultimately thermalize to at least locally be an equivalent to this Gibbs state, and that local equivalence matching the energy density of the pure state with the energy density of this density matrix gives you an effective temperature for the pure state set by the inverse beta. And so one can make the conjecture even a little bit sharper. In particular, the conjecture then says, if a particular Hamiltonian supports finite temperature XY order, and if the effective temperature of my initial starting state for the spin squeezing dynamics is less than the critical temperature for order, then dynamics of the Hamiltonian on top of my initial state will lead to scalable spin squeezing. That's the conjecture. Okay. I'll give analytic intuition and some analytic insights for how to prove, I mean, one can't yet prove all of this, but one can prove certain aspects of it. But before we get there, let me start off with just a little bit of simple numerical evidence. Okay? So the conjecture is a relationship between order, magnetic order associated with a Hamiltonian, and the properties of a dynamical state measured with respect to this type of spin squeezing figure of merit. So let me just take a quick gander into what exactly these two types of things look like. So if one has order, it turns out the standard thing to look at is like an order parameter or the magnetization in the XY plane. So for this Hamiltonian, I've chosen to work in 2 dimensions with a power law that's a little bit weaker than dipolar interactions and with a particular Ising interaction strength that's given by -4. And you find that for this particular set of parameters, the magnetization or the order parameter continually decreases as a function of time starting from my initial product state. So this would say that that initial state does not thermalize to an ordered state at late times. That amplitude of that XY order is decreasing as a function of increasing system size. But there are other parameter regimes, for example, only changing the value of the so-called Ising anisotropy, where one finds that the magnetization, the order parameter, now plateaus to a finite value. That's an example of what something that is ordered looks like as it time evolves forward, as it thermalizes. The same thing you can ask yourself is what exactly does the figure of merit spin, what exactly does spin squeezing, does the squeezing parameter look like as a function of time? In that particular case, I'm now using the exact same parameters that I was showing for the ordered case, it turns out spin squeezing, as promised, it starts off, I should have had an axis here. This is 10 to the 0, which is 1. So the product state starts off with the squeezing parameter being 1, and as a function of time, it gets better. Again, this betterness doesn't say anything. It just means that you have generated some amount of spin squeeze entanglement, but it's not a statement about scalability. In particular, the statement about scalability is that as a function of increasing system size, I switched L and N here, as a function of increasing system size N or L, you should expect that first, there's a time scale that gets larger with system size where the optimal value of the squeezing parameter, the smallest value, is reached. And you can find, indeed, as a function of increasing system size, the time where you find the minimum is increasing. And the dip, the size of the dip, should also improve as a function of system size. That's the scalability of the squeezing as a function of time evolution. So indeed, one finds, at least for this very specific parameter set, that one, with whatever numerics one can do, is able to see some example that is consistent with the expectations that you would get for scalable squeezing. In the opposite limit, you find that a very different behavior. Indeed, there can still be some order 1 amount of spin squeezing generated at early times, but it does not improve with system size, and the location where you see this optimal also does not change with system size. So this is an example of what you would expect for if you had spin squeezing generated at short early order 1 times, but it was not scalable spin squeezing. So now what we can do is very simple. We can take a cut in the phase diagram as a function of Jz, and you can see now the blue curves are represented on the left y-axis over here, and the darkness shows an increasing function of system size. And the red curves are on the y-axis, the xy magnetization. And you find that indeed, for the Jz parameters where there is order, you find that the squeezing parameter improves the system size. For the xy parameters where it sounds there's no order, where it's decreasing, you find that there is no scalable spin squeezing. Okay? So all this is a little bit of numerical evidence that there's something there in terms of the nature of the conjecture about dynamics and relationships to ground or low temperature order. It turns out one can do even a little bit better. One can sort of really try to make a squeezing phase diagram where one starts with this, a variety of different cuts in this alpha Jz plane, and ask, for each of those cuts, starting with the same exact initial state, does one find scalable spin squeezing or not? So one finds a regime with scalable squeezing and a regime with non-squeezing. And it turns out you can use quantum Monte Carlo to ask a very different question, which is the temperature of your initial state below the critical temperature for xy order or not? That's a Monte Carlo question. And we can also generate in quantum Monte Carlo the same exact set of points that relates the xy magnet to the disordered phase. And it turns out, perhaps by this point unsurprisingly, that the two map onto each other quite well. This is true in 1 dimension and 2 dimension, and turns out in 3 dimension, one doesn't really even need a particular long-range interaction, a power law, to be able to generate xy order at finite temperatures. So here, you can already see this relationship just by looking at nearest neighbor interacting versions of the model. Okay. So it turns out that one of the really nice experimental consequences of this is that dipolar interactions in 2D, that dipole-dipole interactions in 2D, typically sitting somewhere in this regime, actually should be able to generate scalable spin squeezing. And I do think this is a really nice point to emphasize that, this type of prediction immediately has a large effect on experimental platforms, because, there's so many different platforms that are dipoles, including ones that really aren't even AMO experiments, the more condensed matter flavored experiments. And so having all of those experiments being able to access, not just order 1 expected gains from this type of entanglement, I think really has kind of changed the landscape of the field, and I'll sort of hope to emphasize that in my last slide or two. Good. So now let me provide a little bit of analytic intuition for sort of what is going on here. So I've emphasized somehow that there's maybe a little bit of a surprisingness to the fact that there's a connection between a very dynamically motivated question about a particular form of metrologically useful entanglement and a question related to finite temperature magnetic order. And so I'll try to give a little bit of analytic intuition by looking at the nature of this particular squeezing parameter. And we'll start by analyzing both the numerator and the denominator. We'll start with the denominator. So it turns out that the squeezing parameter, as I promised you, cares about the length of the vector. If one wants to do Ramsey spectroscopy, one wants this vector to have a large enough length to be able to measure deflections of that. So you care about the way the length of the spin, the total spin in the x direction, thermalizes as a function of time. And perhaps to be expected, starting from your initial product state, if you're in a paramagnetic state, so if you have a temperature for that state such that it's above the ordering temperature, then as a function of time evolution, the length of that vector will slowly shrink. That was where in one of the slides I showed that the size of the XY magnetization as a function of time was going lower and lower and lower, and very, very close to 0. On the other hand, in that same plot on the right-hand side, we showed that the XY magnetization, in some sense the length of this SX vector, was staying the same. It reached some plateau value, which we said was a measure of the order parameter for that system, and that plateau value allows this SX at late times not to get too small. So already at least there's some dichotomy that says that in one limit, in the limit where you're at too hot a temperature, it turns out SX shrinks, and that's bad for the squeezing parameter. And the limit where you're cold, you get to a finite plateau for the order parameter, and that's good for your denominator. The numerator is a little bit more complicated. I think it's actually not, I'll explain it this way because I think there is some nice intuition here, but I will say that I think the correct way to analyze this is actually very much using the language of hydrodynamics of the order parameter to really see what's going on here. But one maybe hint of what's going to happen in that hydrodynamic analysis is actually just an observation that the low temperature eigenstructure of the Hamiltonian for this type of spontaneous symmetry, for this type of XY magnetic order, is very specific. In particular, for this type of XY order, we think about it within something known as the Landau paradigm as a breaking of a continuous U1 rotational symmetry. And it turns out, in that particular context, Phil Anderson, among other things, conjectured that the nature of the low energy eigenstates of that follows something that's often called the Anderson tower. And this Anderson tower of states says that if you look at the magnetization, the Hamiltonian that we have conserves the total magnetization. And if you now simply diagonalize your Hamiltonian in each of the magnetization sectors and look at what is the lowest energy eigenstate, and you ask what is the dispersion of that set of lowest energy eigenstates across all the different magnetization sectors, it looks, certainly numerically, very close to m squared over n. Remembering that m is exactly SZ total, the magnetization is the total magnetization in the z direction, you now see kind of a nice connection. The energy dispersion in this axis looks like SZ total squared over n, which is not unlike the one-axis twisting Hamiltonian. So I think there's probably some truth, but it's hard to make this precise, and I think it's not the full story, that essentially the spectrum at very, very low energies kind of looks like SZ total squared over n, specifically because of the nature of the symmetry breaking that one's getting out, and that actually kind of looks to dynamics that's kind of like one-axis twisting, which is why these systems generate spin squeezing in the first place. Again, I think it's a good heuristic, I think it's not precise. And you can already tell that it's not precise because you ask yourself a question. Is the squeezing that you generate from this type of evolution under this much more general class of Hamiltonians, these long-range XXZ models, is the squeezing that you generate really identical to one-axis twisting? And the answer is no, it's worse. And it turns out that the reason for that is that under one-axis twisting, the area enclosed by the sort of quantum projection noise is unchanged, kind of because you only have the dynamics of one big spin, so it's really integrable in some sense. So the area is enclosed there is unchanged as a function of the time evolution. It's a conserved quantity. But if you evolve, starting from the same product state, and use this long-range XXZ Hamiltonian to generate scalable spin squeezing, it turns out that you will shear the system, but it turns out that as a function of time, the thermalization will cause the overall volume of this projection noise to expand as a function of time because you're no longer integrable. You can think about that in the previous slide as kind of mixing within those different magnetization sectors. And it turns out you can make a very, very simple prediction coming from hydrodynamics for what exactly the scaling of the squeezing parameter should now be. as I said previously, the optimal scaling of the squeezing parameter for one-axis twisting is 1 over n to the 2/3. It turns out because of this extra expansion, this thermalization-induced change of the spin projection noise, you actually get a slightly worse scaling, still better than what you can do with classical correlations, but worse than what you can do with one-axis twisting, and certainly worse than what you can do with the Heisenberg limit. It turns out it's kind of nice, at the end, this is sort of a simple hydrodynamics analysis. You can ask in large-scale numerical simulations, do you see this? And indeed, you do. You find that for, again, this is simply looking at the XXZ model in dimension d equals 1. As you increase the number of sensors, you actually find that at early times, you see a 1 over n to the 2/3 scaling, consistent with one-axis twisting. But at some point, the thermalization dynamics start to matter, and you find a crossover. It's barely 1 decade in X and not even a decade in Y, so it's hard to fit anything to this, but you find something that's not patently inconsistent with the 2/5 expectation that one gets from a hydrodynamics analysis. So it turns out that I sort of hope I've given you kind of a particular snapshot of a connection between dynamics and low temperature order. And it's very natural to ask the question, is it possible that this snapshot is a piece of a larger story? And my answer is both yes and no. It turns out that, for those of you that are a little familiar, perhaps the most natural expectation for what that piece of the larger story might be is maybe a connection between order and metrology that goes through this so-called Fisher information that I mentioned before, which was 1 over c in the classical Kramer-Rao bound. The quantum Fisher information would be 1 over c, I think, double prime in the quantum Kramer-Rao bound. But it turns out that in some sense, the Fisher information is a really good measure of how sensitive a state is to a particular perturbation. And you can very naturally imagine that it really is the variance of that operator in the particular state. And there's also a notion of order, which is represented by long-range order in systems, which is represented by the connected piece of a correlation function. And it turns out, just by literally writing down kind of the English words that describe the two, one immediately sees that the quantum Fisher information is essentially exactly equivalent to the connected piece of a correlation function that often one can use to define long-range order in systems, in many particle systems. And with this connection, you end up getting something that I thought was really fundamental, but I sort of now know not quite to be right, which is that from whether or not the physics of a system at low temperatures exhibits long-range order, a particular type of order known as algebraic long-range order, or is not ordered, one can immediately make some claims about what exactly is the scaling under dynamical evolution of the same Hamiltonian in terms of the metrologically useful states that one gets out from that type of a Hamiltonian. And immediately see there's a 1-to-1 correspondence. When there's long-range order, you get this, you saturate the quantum Kramer-Rao bound. When there's algebraic long-range order, you can maybe beat the classical Kramer-Rao bound, but not always. And if you have no order, then you always are back to the standard quantum limit. This nota bene is very important here. So this connection says that in principle, dynamical thermalization from a pure state to an ordered state can exhibit excellent quantum Fisher information. And that means that the state, the entanglement present in that state, is metrologically useful. But it can be extremely hard to use. In the most general setting, the only way to use it is to evolve your system forwards in time and backwards in time. Backwards in time is very hard, so usually what you do is change the sign of the entire many-particle Hamiltonian, which is also hard to do. So, okay, so there's something that feels like a connection between metrology and order, but I'm telling you it's not exactly the right connection that relates to the spin squeezing discussion we've had, which is also a connection between metrology and order. And how can we visualize that difference a little bit? Sorry, I'm almost done. Turns out one can plot just as a function of time what exactly the dynamics of the squeezing parameter are. Here I'm plotting 1 over the squeezing parameter so that improvement is represented by increasing, and the quantum Fisher ratio was similar. As promised, at a time that scales extensively with system size, for those of you that remember, it was n to the 1/3, the squeezing parameter reaches optimal and then gets worse. It turns out that the quantum Fisher information has not reached its optimal at that point yet. Here we're thinking specifically about the one-axis twisting model. In fact, the quantum Fisher information keeps improving and improving and improving, and actually gets to a state over here known as the Dicke quantum state, which saturates the Heisenberg bound for sensing. but it's not the squeeze state. It turns out that because of the kind of integrability of this model, if you look at the dynamics, it just keeps repeating like this. In the context of the XXE model, you can see that there's something different because what happens is that, well, the squeezing parameter gets optimized at a later time, but as a function of time, and indeed, the Fisher information also gets better, but as a function of increasing time, you find that at late times, thermalization still leads to a very technically useful metrologically entangled state because the quantum Fisher information allows, but by that point, there's no more spin squeezing. So it turns out that the previous slide, although it's kind of powerful and gives you this connection, is maybe not the right way to view the connection of spin squeezing. And it turns out, as Ivan kind of pre-mentioned, the mathematical underpinnings of the connection between U1, continuous spontaneous symmetry breaking, and this type of metrological use of entanglement really can be analyzed in terms of looking at hydrodynamics of the order parameters. And there, actually, you end up getting really a huge classification of all of the different types of models. And this, I think, is really special. You know, previously, the models that exhibited scalable spin squeezing were all-to-all coupled 1-2-axis twisting models. But now, from this understanding with respect to hydrodynamics, there's just, you know, any number of models can exhibit this type of scalable spin squeezing. And even, we focused on the first one, the first row here, which has one squeezing mode. It turns out there are multiple examples of Hamiltonians which have different squeezing modes, so you can make measurements of non-commuting observables, and both of the measurements in the different quadratures can be better than any classically allowed measurement. So that would be the case if you have multi-mode squeezing, or squeezing of multiple degrees of freedom. And I should emphasize, maybe just two last slides, this has had a kind of almost immediate impact on experiments in a really special way. So the Brouwers group was one of the first people to sort of notice this and sort of start looking at scalable spin squeezing in their electric dipoles. They have an electric dipole in an atomic system, and after them there was squeezing in optical lattices, squeezing in an erbium gas microscope, and actually some of my own group's work, squeezing in a solid-state system of color centers as well. So with that, let me thank you for your attention and acknowledge all of the people that worked on this, especially Max and Beanton on the theory side, as well as Emily and Marcus and our experimental collaborators in the Brouwers group. Thanks a lot.
Thank you, Norm.